Okay, perfect. Welcome everybody to another MCRN Colloquium. Today we're very fortunate to be joined by Dr. Paul Ritchie. Paul is currently a research fellow in the Mathematics and Statistics Department at the University of Exeter in the UK. His research specializes in climate tipping points, something certainly of interest to most of us, but with a particular focus on the dynamics of rapidly forced systems and the conditions under which some systems may exhibit overshoots or undergo such rate-induced tipping. So very much looking forward to the talk. And with that, Paul, please take it away.
Great. Well, thank you, Christian, and thank you for the invitation to present in this series. So today I'm going to be talking about some joint work that we've currently got under review. So we're very open to any feedback that you might have. And this is joint work with Peter Ashwin, who's also at Exeter, and Robin Bastiansen and Anna von der Heet at Utrecht University in the Netherlands. So today I'm going to be focusing on the role that coupling and timescales has in the framework of interacting tipping elements. So firstly, what do we mean by a tipping point? Well, we typically associate a tipping point being the moment in the forcing where if we go beyond it, we observe this an abrupt and often irreversible transition from one state to another stable state. Now, there's various elements of the climate system that could be susceptible to undergoing tipping under global warming. And so these have been depicted on this world map on the left-hand side. It's very similar to some other maps that you might have seen like this, and it includes various elements such as large-scale ice sheets, the melting of those, disruption to ocean circulation currents, or dieback of the Amazon rainforest, as well as disruption to monsoon systems. Now, not only do we have to be concerned about these different elements on an individual basis, but there's belief that these elements could also interact with one another. And one element tipping could therefore lead to the destabilization of another element and potentially cause that to undergo tipping. So one common chain of events that we may discuss in the literature is the melting of the Greenland ice sheet. This could add large amounts of fresh water to the North Atlantic, and this AMOC circulation, so an ocean circulation current in the Atlantic, relies on the salinity gradient in the North Atlantic, where we have salty surface waters and fresher bottom waters where we have this overturning. But if we add fresh water to the North Atlantic from the melting ice sheet, this could weaken this salinity gradient and therefore disrupt the overturning and lead to a collapse of the AMOC. Now, an AMOC collapse could alter weather patterns, and so this might also have implications to the Amazon rainforest or the West African monsoon. And these elements not only operate on different spatial scales, but they also operate on different temporal scales, which is going to be like a main focus of today's talk. So, for example, we've got that Greenland ice sheet that operates on the order of millennia, and then the AMOC may be more like century or so, and then the Amazon rainforest could be on the order of decades. And so this is what we would term an accelerating cascaded tipping elements, because the further you get down that chain, the faster these elements are responding. And so we're going to be looking at these accelerating cascades, but from a conceptual modeling point of view. So to start with, let's just consider a single 1D non-autonomous system where we're modeling the change in some state variable x. So this could be tree fraction if we were thinking of the Amazon rainforest, or it could be the strength of the AMOC. And then this is modeled by some function f, which depends on our state variable x and our external force in capital lambda. So this f, we're just going to assume, takes our classical double-fold bifurcation structure. And then we're having this lambda parameter, which acts as our external forcing, and it takes this tangent-like function where we start at some initial level lambda minus, and then we ramp up to some final level lambda plus, and the rate at which this change occurs is governed by this rate parameter r. And for the purposes of this talk, we're going to assume that this is always very small, and so we're in the classical setting of where we might be considering a slow passage through a fold bifurcation. Now we can introduce some terminology that will become useful later on, we can say that we will have tracking of our system if our final finishing level, lambda plus, is below some critical threshold in our external forcing, which corresponds to a fold bifurcation. So if we look at this orange forcing profile, we just have a small change in that forcing. And then so if we start on this lower stable branch, you can see that we just track that branch. But then if our forcing goes beyond this critical threshold, then we're going to have bifurcation induced tipping, or B tipping, where we cross the fold bifurcation and then our system abruptly transitions to this alternative state given by this blue profile. And so this is our first system that we're going to consider. Now we're going to couple it to a downstream system, where we're always actually going to give the same external forcing to this upstream system, and that's going to be this blue forcing profile that you see here. So we're always going to be tipping our upstream system, and then what we're going to be interested in is looking at the behavior on the downstream system based on the coupling between the upstream and the downstream and the respective timescales of the two systems. So this is our full system that we're considering. So I've just got a block diagram to try and illustrate our setup here. So like we've seen before, we've got some external forcing that's feeding into our upstream dynamics. And then we have a coupling function M, which takes the output of our upstream dynamics and feeds into our downstream system, which is given by this other differential equation, y dot. Now here I've got a G, but for the purposes of this talk and for simplicity, we're just going to assume that this G is the same as our F, that we have this double fold bifurcation structure for our downstream system as well as our upstream system. And then we have finally this epsilon parameter, which governs the timescale separation between the upstream and downstream dynamics. So if epsilon is very small, then our downstream system is relatively fast compared to our upstream dynamics. And so we're in this setting of an accelerating cascade of tipping elements. Whereas if our epsilon parameter is very large, then comparatively the downstream system is much slower than the upstream, and therefore we have a decelerating cascade of tipping elements. Now, again, for the purposes of this talk, we're going to mainly be focusing on an accelerating cascade. So we're going to have epsilon chosen to be fixed and very small, but at various intervals I will discuss how the behavior that we observe might change for a decelerating cascade instead of an accelerating cascade. Okay, but before that, we can now define some behavior that we might expect to see for our downstream system. So this coupling function M of X is essentially the effective forcing on our downstream dynamics. So if we call this mu, and then we define our M plus, so our final finishing level for the effective forcing on the downstream dynamics, to be our mu in the limit t tending to plus infinity. And then we can say that we're going to have downstream tracking if the supremum of our mu is less than our critical threshold in that forcing, lambda u. Then we're going to have endpoint tracking where we just stay on this lower branch of the downstream system. But then if our forcing level finishes beyond the critical threshold, then we will have B tipping to our upper stable branch for the downstream system. But then we can have this third case where we can actually have an overshoot. And this is meaning that we have our final forcing level to be below the critical threshold, but there exists an R and a T such that our mu does briefly go beyond this critical threshold lambda u. So when we have a temporary exceedance of our critical threshold, this is what we call an overshoot. And then depending on the R and the corresponding epsilon, we can either get bifurcation induced tipping or endpoint tracking. And so we're going to look at what types of coupling might actually create this overshoot behavior, as well as, again, looking at the timescales and whether we would get bifurcation-induced tipping or endpoint tracking. Now, before we go into any examples, let's consider the different possible tipping sequences we might expect to observe.
I think you have a question in the chat.
Yeah, so go for it. Sorry, I can't read the chat or anything, so if someone could read it.
Yeah, well, this wasn't in the chat, but I was just wondering, sorry to interrupt, this is Kate.
No.
I was wondering in the previous slide, what the R, is that connected to the previous setup? I just lost what the R is.
Yeah, so the R parameter is the rate parameter in our external forcing.
Okay,
so we're
right.
typically going to assume that to be slow, and it's also fixed. So it's not too important, but we're just essentially having a slow passage through the fold bifurcation of our upstream system.
Okay, wonderful. Thank you.
No worries. Thank you. Yeah. Okay. So these are the different types of tipping sequences we might expect to see. So one could imagine if the coupling between the upstream and the downstream system is very weak, then we will tip the upstream system because we're giving it that same external forcing, and there's no back coupling from the downstream to the upstream. So we're going to have tipping of the upstream system, but tracking of our downstream system. So this is the first case. Now I should indicate these block bars indicate the duration of the tipping of that respective process. So at the start of the bar, this is to indicate when we have the onset of the tipping, and the end of the bar is the offset of the tipping. And because, again, that forcing on the upstream dynamics is always the same, this blue bar is always going to remain fixed. And then it's how the downstream dynamics or the tipping of the downstream system moves relative to this blue bar. Okay, so the next two cases are probably what we typically associate with cascades of tipping elements. So we cross our threshold for the upstream system. This causes that upstream system to undergo tipping, and that makes us approach the threshold for our downstream system. And then we can either cross the threshold for our downstream system after the upstream system has finished tipping, maybe through some subsequent change in the external forcing, or actually during the process of the upstream system undergoing tipping. The next two cases are where we might actually start the tipping of the downstream system before the upstream system. So you could imagine if we were maybe very close to the downstream threshold compared to the upstream threshold, then only a small change in the upstream dynamics might be enough to actually cause us to cross the downstream threshold before our upstream system undergoes tipping. And so all these cases so far can appear in both accelerating and decelerating cascades. The final two are unique to either an accelerating or decelerating cascade. So this first one is where we have downstream tipping completely contained within upstream B tipping. And so here what we're seeing is that we cross the upstream threshold, that starts tipping, and in that process we cross the downstream threshold, but in an accelerating cascade, our downstream dynamics are much faster, and so that tipping occurs very quick, that downstream system might completely tip before the upstream system has finished tipping. And then we might get the exact opposite behavior for a decelerating cascade. Again, if we're starting quite close to the downstream threshold and we cross that first, now because the downstream system is much slower than the upstream, that the upstream system could completely undergo tipping during the downstream system undergoing tipping. Okay. So the first case we're going to consider is arguably the simplest form of coupling, where we just have some linear coupling. So here we're just going to assume for simplicity again that our A parameter is 0. And then this B parameter essentially determines the strength of the coupling between the upstream and the downstream dynamics. So you can see we're just multiplying this coupling parameter B by the change in our upstream output. And then on the right-hand side here, we've got the external forcing for our upstream system plotted on the x-axis. And on the y-axis, we've got our effective forcing for the downstream dynamics. And then as we're using the same drift term for both the upstream and the downstream dynamics, we have critical thresholds at +2 for both. And so these are indicated by these black dashed lines. And so as we increase our external forcing from 0 to 4, you can see that in this weak or relatively weak coupling case, we first cross the threshold for our upstream system. That then undergoes tipping. This causes a rapid increase in the forcing of our downstream system. It approaches our downstream system, but then downstream threshold, sorry. And then our upstream system has finished tipping and it's stabilized to its new state. And so our forcing essentially stabilizes below that downstream threshold and we don't cross it. And so here, what you're seeing in our 3D bifurcation diagram, where we've got the external forcing coming towards us, we've got the upstream state variable on the horizontal axis and the downstream state variable on the vertical axis. If we start on this lower stable branch on the left-hand side, now this corresponds to the untipped upstream and downstream state. We then track this stable branch until we hit a fold bifurcation at lambda equals 2. We then start tipping our upstream dynamics. So you can see that the trajectory of this, the color of this trajectory changes to a lighter shade of blue. That's to indicate the faster dynamics of the tipping behavior before we then converge to this intermediate branch over here, corresponding to the tipped upstream system, but untipped downstream system. And then we stabilize our system on this equilibrium branch. But if we were to increase that coupling strength a little bit further, now you can see that we will subsequently cross our downstream threshold. Although here, we're not crossing it in the process of the upstream system undergoing tipping. It's only the subsequent change in the external forcing that is still being fed into the upstream system, but there's ultimately still going to be some small changes in our upstream output, and that's enough to take us past the downstream threshold. And so this is where we have downstream B tipping after upstream B tipping. So again, we start on this lower branch, we cross the fold bifurcation, we tip our upstream system, we converge to this intermediate branch, but then we hit another fold bifurcation, and that causes the tipping of our downstream system. And again, this trajectory changes to an even lighter shaded coloring, again, because we're in this accelerating cascade where our downstream dynamics are even faster than our upstream dynamics. If we increase that coupling strength further, now we get the more traditional setting where we cross the upstream threshold and the upstream system undergoes tipping. And in the process of the upstream system undergoing tipping, we cross the downstream threshold. And so you can see now in the bifurcation diagram, we don't reach any intermediate state. We just tip straight to this final branch on the upper right. But this is also where we're now having downstream within upstream B tipping, because you can see as we cross the fold at lambda equals 2, our upstream system starts tipping. We then cross that threshold for the downstream system. Our downstream system undergoes tipping very quickly, again, because of the faster timescale. And then after the downstream system's finished tipping, that upstream system continues tipping until we reach our final destination. And so we're going to have this downstream within upstream B tipping scenario until the coupling strength gets so strong that we have this special case where we have a simultaneous crossing of our thresholds for the upstream and downstream systems. And so here what you can essentially see is that we cross one fold bifurcation at lambda equals 2. Again, because essentially both systems undergo tipping at the same time, but because again the downstream dynamics are much faster, we essentially tip up vertically and we land on another fold bifurcation and our upstream system undergoes tipping. But then if we increase the coupling strength even further, now we can actually cross the downstream threshold before we cross the upstream system's threshold. So now we're crossing the fold bifurcation before we get to lambda equals 2, and we converge to this other intermediate branch on the upper left here, where we have the untipped upstream system, but tipped downstream system before we then cross the upstream threshold and the upstream system undergoes tipping. Now, this scenario in particular actually raises interesting challenges for causality approaches, because if we were to observe this in the real world, where the downstream system tips and then we see the upstream system undergoing tipping afterwards, we might think that the downstream system has caused the upstream system to undergo tipping. But we know in our model setup, we have no coupling from the downstream dynamics to the upstream system. And so therefore, there's a challenge of whether causality approaches could be able to actually distinguish this from the traditional sense of tipping cascades, where one upstream system has actually caused a downstream system to undergo tipping. Okay, so let's maybe now unfold the dynamics in a bit more detail of what's going on here. So we're again back to our weak coupling strength case. And on the left-hand side here, we've got a projection of our bifurcation diagram, where now we're only looking at the state variable for the downstream system on the y-axis and the external forcing on the x-axis. So again, we've got this third axis, which we saw previously, but you can't see in this projection for our upstream dynamics. But we're using this projection because we can actually quite nicely visualize in 2D all our steady states. So here we have 9 steady states, which is the maximum number of steady states we can have because we've got a cubic polynomial for both our upstream and downstream systems. And these steady states are separated by 8 fold bifurcations. And these fold bifurcations are plotted on the right here in this 2-parameter bifurcation diagram, where we've got our external forcing on the x-axis and our coupling strength on the y-axis. Now you'll notice these vertical lines change thickness. So when the line is very thick, that's when we have 3 fold bifurcations at that particular value of lambda. But when it changes to a thinner width, we only have 1 fold bifurcation. And we'll discuss how that actually occurs. And so I've also shaded this gray region to indicate the range at which we're changing our external forcing over. So we're starting at lambda equals 0 and we're going up to +4. So as we saw for this weak coupling case, we're starting on this lower stable branch. We hit a fold bifurcation at lambda equals 2. The upstream system undergoes tipping, which causes a small change in the downstream system, but we converge to this intermediate branch and stabilize before a fold bifurcation over here on the right. Now this far right fold bifurcation corresponds to this curve that is coming in from the right-hand side here on the 2-parameter bifurcation diagram. And although we're on a log scale here, you can see that we don't need to increase our coupling strength very much before this fold bifurcation will drop below lambda equals 4. And then once it does drop below lambda equals 4, this is going to open up that possibility to have downstream tipping after the upstream tipping. So as we increase that coupling strength, you can see that's exactly what's happened. This fold bifurcation is now below 4, and so we also tip our downstream system as well. And so as we increase this coupling strength even further, this fold bifurcation will continue moving to the left. And so once that fold bifurcation has got below lambda equals 2, then our system cannot tip to any intermediate branch, and so we then end up with that downstream within upstream B-tipping scenario. And then as we continue increasing that coupling strength, this fold bifurcation will move all the way towards lambda equals -2. It will have these two folds, neighboring fold bifurcations. They will also approach each other vertically. And so we'll have 3 fold bifurcations that will all collide, and they will just leave 1 fold bifurcation. And then this fold bifurcation will then start moving towards the right. And so as I jump to the next coupling strength, you can see that's exactly what's happened, where we've now got no intermediate branch to converge to, and these 3 fold bifurcations have all converged into 1 fold. And then as we increase that coupling strength even further, this fold bifurcation will move towards lambda equals 2, and then we get exactly the same dynamics happening again, where the 2 neighboring folds will also approach each other vertically, such that we get the 3 folds all colliding and leaving just 1 fold bifurcation. Now, this is the case for where we had that simultaneous crossing of the thresholds. Now, you might expect this would occur at when we had this collision of the fold bifurcations at lambda equals 2. But there is a slight offset, and that is because of transient effects. And this is, and essentially it's down to this selection of a non-zero R parameter, which is that rate parameter in our external forcing. So in the limit R tends to 0, we would expect this simultaneous crossing of the thresholds to correspond to this intersection at lambda equals 2. But the larger our R parameter, the larger this offset will be. Now, as we increase that coupling strength to even stronger levels, this fold bifurcation will move towards the left, and then this will open up that possibility for us to converge to this intermediate stable branch where we tip our downstream system before the upstream system. So that's exactly what you can see here. We're tipping to this intermediate branch, and then we're hitting a fold bifurcation at lambda equals 2, which causes our upstream system to undergo tipping. Okay, so now we can summarize this in a tipping regimes diagram for this linear coupling. So on the x-axis, we've now got our coupling strength parameter B, and on the y-axis, we've got our timescale separation parameter epsilon. And so what we've just walked through is the setting of an accelerating cascade. So essentially a horizontal cross-section near the lower half of this plane. So we saw that for weak coupling, we would have upstream B tipping, but downstream tracking. Then there's a small interval where we get the downstream system tipping after the upstream system. But we have a much larger interval where we have this case that's unique to accelerating cascades, where we have downstream within upstream B tipping, before very strong coupling strengths, where we might actually cross that downstream threshold first, such that the upstream tipping only occurs after the downstream B tipping. So now we might want to ask, how does this change for decelerating cascades? So now the downstream dynamics are much slower than the upstream dynamics. Well, for sufficiently weak coupling strengths, nothing changes. We still obviously will have upstream B tipping and downstream tracking, or downstream occurring after the upstream. But where we had downstream within upstream B tipping for accelerating cascades, well, we can no longer get that because the tipping dynamics on our downstream system are now much longer. And so therefore there has to be an overlap. But once the onset of our downstream tipping occurs before the onset of our upstream tipping, we can get the exact opposite, where we have upstream within downstream B tipping. So again, we've got the downstream system starting its tipping. We shortly afterwards cross that upstream threshold, but because that's now comparatively fast to the downstream system, that completes tipping during the process of the downstream system undergoing tipping. Okay, so that was linear coupling. The other type of coupling I want to discuss is a localized state coupling, which is given by this coupling function, this Sech function. And this is designed to mimic a coupling via the flux of the upstream system, or essentially the derivative. And so the main motivating example we're thinking of here, in the climate at least, is the coupling of the Greenland ice sheet to the AMOC. So it's not really the amount of fresh water that's been added to the North Atlantic that determines whether it collapses or not. It's really the rate at which fresh water gets added that determines whether it will tip. And so under such a scenario, well, I should say again, we're going to again assume that our A parameter is 0 and the parameters C and D are fixed. And again, we're only going to be varying our parameter B, which again acts as the coupling strength for this localized coupling. So on the right-hand side here, again, we've got our external forcing, or the forcing for the upstream system on the x-axis, and this localized state coupling, or the forcing for the downstream dynamics, on the y-axis. And so you can see in this weak coupling case, we again cross the upstream threshold first, and then as the upstream system starts undergoing tipping, this causes us to have an increase in the effective forcing of our downstream forcing, but then the upstream system reaches a maximal rate of change before it then starts to converge to its alternative steady state. And so that rate starts decreasing. So the effective forcing of our downstream system reduces back down to original levels. And so in this case, we're never actually crossing that downstream threshold. So what we're seeing in this bifurcation diagram is very similar to the linear coupling case for at least weak coupling, where we start on this lower stable branch, we hit our fold bifurcation at lambda equals 2, and we tip our upstream system, and we converge to this intermediate branch on the lower right here. Now, if we increase that coupling strength a bit further, we get this special case where we just graze the downstream threshold, but never cross it. And in terms of the behavior we see of our system, we get pretty much identical behavior where we just tip our upstream system, but don't tip our downstream system. Now, for even stronger coupling, we can actually have this brief exceedance of our downstream threshold. And so this is where we're now having a brief overshoot of our downstream for our downstream system. But in this scenario, we've got a sufficiently fast reversal in the forcing for our downstream system that we can actually still prevent it tipping. So we still have endpoint tracking for our downstream system, but we have B tipping of our upstream system. So you can see we cross our fold bifurcation at lambda equals 2. We then do briefly cross this downstream threshold, and that looks like it's going to cause our downstream system to undergo tipping, but that reversal in the forcing is sufficiently quick that we can actually pull it back, and only our upstream system undergoes tipping. But you'll notice that this coupling strength is very precise, and that's because we're right at that critical coupling strength, where if we were just to increase it that little bit further, now we would actually have tipping of our downstream system as well, because that reversal in the forcing for how far we're overshooting the threshold is no longer sufficiently quick to prevent the system from tipping. But you can see that dynamically, nothing's really changed except from the behavior of the system when now we are converging to this upper right stable branch where we've tipped both the upstream and the downstream threshold systems. Now, increase that coupling strength even further, we have obviously much larger overshoots and for a longer duration. So we will definitely get tipping of our downstream system. And this is where it's actually quite clear where we now got this, again, downstream within upstream B tipping scenario, because again, we're back in this accelerating cascade setting. So we again cross the upstream threshold, subsequently cross the downstream threshold, and the downstream system undergoes tipping very rapidly. And then the upstream system continues tipping to this final steady state. Again, we're going to get this until we have our simultaneous crossing of our thresholds. And just like with the linear case, we tip from one fold bifurcation onto another fold before we tip to our final state. And then also, just like the linear case, we can have the coupling get sufficiently strong where we may still cross our downstream threshold before we cross the upstream threshold, where we again converge to this upper left stable branch or intermediate branch before our upstream system subsequently undergoes tipping. Now, another thing to point out here is that the coupling strength is so large that our forcing for our downstream dynamics actually never gets back below the threshold for a downstream system. So we no longer class this as an overshoot because we have a continual exceedance of our downstream threshold. Okay, so again, let's now look in a bit more detail of how this is unfolding dynamically. So we've got three very similar structures occurring here. And in this projection, it's not so nice to visualize. So I'll try and describe what we're seeing. Again, we've got a steady state that's coming in from the far left. And that continues until we have a fold bifurcation at lambda equals 2. And so we get this wrap round where we have now a steady state extending back to lambda equals -2 before we have another fold bifurcation and another steady state appearing, which then extends all the way to the far right. And so that is a very similar picture that we see for all three scenarios here. And so for this weak coupling case, we have 6 fold bifurcations where they are where we have 3 fold bifurcations at lambda equals -2 and 3 fold bifurcations at lambda +2. Now, as we increase this coupling strength, these teardrop-like shapes, they will move together vertically and will touch when we have that grazing of the downstream threshold, and then they will break away and form 2 new fold bifurcations. And then, and so again, this is now where we're at that critical coupling strength, where we still just about have downstream tracking, but for that slightly stronger coupling, we then get tipping to our alternative branch. And again, dynamically though, nothing really has changed. Now, as we increase our coupling strength further, we will see this fold bifurcation moving towards lambda equals 2, where it corresponds to this segment of the curve. Well, this fold bifurcation, just like in the linear case, we will have 3 fold bifurcations all coming together and colliding and leaving just 1 fold bifurcation, which will then start moving off to the right as well. So as we jump to that case, you can see that's what we have, where we're now again within this regime of downstream within upstream B tipping, where we're not converging to any intermediate state. We're just tipping straight to our final equilibrium branch over here. Now, as we increase the coupling strength further, this fold bifurcation will just continue racing off towards plus infinity, while this fold bifurcation will again collide with these other 2 fold bifurcations, leaving just the single fold bifurcation. And so again, this is our case where we had that simultaneous crossing of the thresholds, where you can see maybe more clearly, we've got this offset between the collision and where this coupling strength corresponds to. Again, this is due to the transient effects in our external forcing. And then, just like the linear case, as we increase that coupling strength further, this fold bifurcation will move to the left, opening up that possibility where we can tip to this intermediate branch before we cross the fold bifurcation for our upstream system and tip our upstream system. And so how does our tipping regimes diagram look? So again, for these accelerating cascades, we have, for very weak coupling, we just have tracking of our downstream system and only upstream B tipping. Now for accelerating cascades, it's actually very difficult to have an overshoot of the downstream threshold without causing tipping, because the dynamics on the downstream system are very fast. Any real noticeable overshoot of the threshold will actually still likely cause tipping of the downstream system. And so we have a very large region where we have this downstream within upstream B tipping. And then once the coupling strength gets sufficiently large, we have upstream B tipping only occurring after downstream B tipping. And this roughly corresponds to also where we have the end of this overshoot period and instead just a continual exceedance. But you can see for decelerating cascades, this regime of just upstream B tipping expands much further to the right here. And that's because when we've got decelerating cascades, our downstream system is now much slower. And so that really does offer that opportunity where we can actually briefly overshoot a threshold, but by a sufficiently fast reversal in the forcing, actually prevent our system from undergoing tipping. But ultimately, this boundary will asymptote to where our overshoot ends. So if we do have a continual exceedance of our downstream threshold, then we will ultimately get tipping of our downstream system. But again, we get the opposite behavior primarily, where we have upstream B tipping within downstream B tipping, again for the same reasons that we cross that downstream threshold first, but then the downstream tipping plays out over a much longer time scale compared to the upstream system. And then finally, we developed some theories, so myself and Jan Sieber back in 2019, that linked how far we maximally exceed a threshold and for how long. And these were found to be linked in an inverse square law. And so we can plot this theory for this downstream system overshoot. And this is given by the red dashed line. And you can see that we've got a very nice agreement between the theory and the numerically calculated critical boundary. And so just to summarize, we've identified and introduced criteria for different tipping regimes we might expect to see in this framework of coupled systems. We also specifically introduced this idea of where we might have downstream within upstream tipping, where the downstream tipping dynamics take place entirely within the upstream tipping event. And so this is only applicable to accelerating cascades, whereas for decelerating cascades, we could have the opposite behavior where upstream B tipping is completely contained within the downstream B tipping. We then also noted that this interesting challenge for causality approaches, where if we saw the downstream system tipping before the upstream system tipping, could causality approaches actually determine that the downstream system hasn't necessarily caused the upstream system to undergo tipping, whereas in a typical cascade, that might well be the case. And then finally, we considered this idea of a localized state coupling designed to mimic a coupling through the derivative or the flux of our upstream system when we think of the Greenland ice sheet coupled to the AMOC. And this raised the possibility of having overshoots of the downstream threshold, which may be able to avoid tipping, especially if we're in a regime of having a decelerating cascade. And so with that, I would like to thank you for your attention, and I'm happy to take any questions.
Okay, great. Thank you very much, Paul. It was a wonderful talk, really interesting. So yeah, I guess if we'd like, we can click the clapping emojis and all. And then, yeah, we have enough people here. So I guess, yeah, if you've got a question, please raise your hand. And I think, let's see, maybe I can look at the queue here. There's quite a few. So
Question.
Sure, go ahead, man. Yeah, and then
Unless anybody else has questions. Oh, wait.
I think I saw Luis raise a hand first, maybe.
No, not.
Oh, you were looking for the clapping emoji. Yes, they do look kind
Yes,
of
I was.
Sure. Okay, then sure, go ahead, Emmanuel. Yeah.
Okay, so one thing that you mentioned when you do those systems that's important that I didn't see you talk about is this timescale separation.
Yes.
Is there a timescale separation between the two systems that plays a factor into the tipping?
Yeah, exactly. So the timescale separation was given by that epsilon parameter. So most of my talk, I was considering that epsilon parameter to be very small. And so that's when we were in that regime of having an accelerating cascade. So I don't know if you remember where that epsilon parameter appeared, but it was essentially on the downstream dynamic. So we had epsilon y dot equals f of x, f of y, comma m of x. And so when epsilon is very small, we would have fast dynamics on the downstream system, but slow dynamics on the upstream. And so, yeah, based on that timescale separation between these two systems, you can get these different types of tipping behavior that I was trying to, elaborate on.
But it does play a factor, that's correct?
Yes, yeah. On the downstream system. So it's not changing the behavior on our upstream system. It's the epsilon parameter is essentially changing how the timescale of the downstream system is different to the timescale of the upstream system.
But when I say play a factor on the different scenarios that you have.
Yes. So if that epsilon parameter is very small, then it's possible to get downstream tipping within upstream B tipping. But if it's very large, then you can't get that behavior.
Got it. All
Yeah.
right. Thank you.
Thanks.
Great. Yeah, I think Hassan, you have a hand up.
Yeah, thanks, Paul. Very nice talk. I think after a few times of seeing the talk, I finally kind of have a bit of understanding there. So a question about this table that you have, what like tipping in upstream and downstream at the start. Would it be possible to have tipping in the downstream without tipping in the upstream, or you eliminate this case?
We eliminate this case for this particular study because we're always considering the same external forcing on our upstream system. But you could imagine maybe the simplest case would be where we had that crossing of the downstream threshold before the upstream system. If we then sort of stopped that external forcing straight away, then we would never actually cross that upstream threshold. Another interesting example I've often thought about, but I haven't actually looked into, is if we have an overshoot profile in on our upstream system, and if our upstream system is slow, you could imagine we could cross that threshold and get back and not tip the upstream system. but then there will be some changes to the upstream system, and that might be enough to cause us to cross the downstream threshold. And if the dynamics on the downstream system are very fast, your downstream system could undergo tipping. But I haven't actually looked into that scenario as of.
Also, in your linear coupling formula, you have this parameter A. I think if you fix it to 0, but if you change A, you might cross a bifurcation for the downstream system before you.
Yeah. So
yeah.
I mean, I guess that A parameter can essentially determine how close you start to the downstream threshold in the first place. Yeah.
Okay. Thanks.
Yeah, Kate, please go ahead.
All right. Yeah, thank you, Paul. I enjoyed your talk. And yeah, that was really interesting. The part about the like causality, like having something downstream tip before it's trigger upstream. Yeah, that is really cool. I was wondering, like for the different like bars of like time intervals when we're tipping, like kind of how you chose a definition of like that time interval, and if you were thinking about like kind of observable things, like things that people would observe in the climate system.
Yeah, no, very good question. So for the onset of the tipping, we just essentially choose the bifurcation. Once we cross the fold bifurcation, obviously with the downstream system, it might not. It can cross that fold bifurcation, but not undergo tipping. So obviously in that case, we discount it. But if it does undergo tipping, we say the onset is when we cross the threshold for that respective system. Now, so that's a threshold in the effective forcing of that respective system. For the offset, or when the tipping finishes, we essentially define a threshold for the neighbor once you get like within the neighborhood of the alternative steady state. So it's essentially a threshold in your state variable. That is a bit more arbitrary in terms of how you choose it, but we've been looking more recently about how sensitive that is, and it doesn't really change those boundaries that we plot in those tipping regime diagrams, but yeah, it is arbitrary how you sort of especially define that offset.
Yeah, could I make a comment?
Yeah.
Yeah, I wonder if like in the models that you've shown us, we kind of have like perfect knowledge of where the branches are and where the bifurcations are and stuff. But I wonder whether if somebody's like looking at a time series of like, I don't know, some indicator of AMOC strength or something else about, like Greenland melt rate, things like that, if like what people might observe could be related to like rates of change, and if there's a way to look at like changes in rates of change or something like that, or I don't know if that would like tie it to observables.
No, quite possibly. There is a lot of discussion in the literature in terms of classifying whether a system, how can you determine whether a system has actually tipped or not. Right. So like you've said, the aim, does it have to reach a certain circulation strength, once it gets below a certain level? But like you say, looking at rates of change in a variable could also be another metric that could be used. Yeah.
It's maybe kind of naive, like things can move quickly without doing like a bifurcation tipping, but yeah, just an idea.
Yeah, thanks.
Great. Any other questions for Paul? Okay. If not, we can set him free, and of course thank our speaker again. So starting emoji, and thank you very much, Paul, for a wonderful talk. And I think we do all have a talk next week, so see you all then.
Cool. Thank you.
Thank you.
Thanks, Paul.
Cheers.